Last example, we're going to write out a decay series. This case we have thorium-226 decay to acetane-214 through an alpha beta alpha alpha decay. What we're going to do is write out the decay series. So we're going to write out the 4 reactions. What we're doing is we're starting off with thorium-226. So thorium, when you look on the periodic table, is element number 90. So we'll start with the first equation, thorium-226. And what we're going to start with is an alpha decay. So 4,2 alpha. And then figure out what the other particle will be. When you balance the top numbers, we're left with 222. Balance the bottom, we're now left with 88. Look up element 88 on the periodic table, and element 88 is radium, Ra. So there's the first step. We've done our alpha. Now we're going to do a beta. So radium 22288 is going to undergo beta, and again, unless you're told beta positive, you assume it's the electron because that's the one that occurs naturally. And what we're going to be left with, again, you balance the top numbers, 222 nucleons. Balance the charge, we're left with 89. And when you look up 89 on the periodic table, we get actinium, AC. There's our beta. Now when you kick out a beta, don't forget you get an anti-neutrino. Got to include that. Now we get an alpha. So 222, 89, actinium, alpha decay, 4,2 alpha. Again, balance should give us 218 and 87. So if you look up element 87 on the periodic table, that's francium, Fr. No neutrinos or antineutrinos with alpha decay. And then do our last one, 218 francium is also going to undergo an alpha decay. And what are we left with? Well, 214, 85, 80. So there's the decay series listing the reactions in this example. Every element above basically lead goes through some sort of decay series to eventually become lead. In this case, there was 4 reactions. The example I have in your notes of uranium was a series of many, many, many reactions to eventually end up as lead. Now the weird thing is, when you actually measure this, some particles may be at step 1, 2, 3, or 4. Other particles may have not even started. It's actually quite weird in terms of actually trying to predict which nucleus goes when. In fact, we don't even do that. What we do is we just have a measure of the time it takes for half of them to eventually go. Do we know specifically which half or which ones? Of course not. But we're just assuming that half of these nucleus eventually decay in this particular instant of time, and you'll see that when we get to a later lesson where we start to measure half-life and radioactive decay.